All right, let me try to. Yeah, we did a lot of Matlab demonstration videos, but let me try to do a class with this online thing. See if it works. I'll ask if you like it or not. So let's start. I'm the plan is that I'll cover what I want to cover about random variables. This is the last piece of it via this online lecture. Then when we get back to class, we can talk about the next topic, which is the functions of random variables. Okay, let's get started. Just recap. What have we learned so far? First of all, we play some like math games about randomness and chance. We know things can be random. Then we know if we can represent things with some numerical value, then we can model them with some mathematical models. We specifically call those things random variables. We talk about how to represent them, like their mean, standard deviation, moment stuff, and then you have data, how to calculate those. And then next step, we introduce some classic mathematical models people use to represent random variables. Those are the tools you can use, right? There's discrete random variables, there are continuous ones. And then we have different distributions, and we know that doesn't matter what you are, if you are a random variable, you have a CDF, cumulative distribution function. If you can get that, you can get all other functions or property of this random variable based on that. So in fact, in Matlab, there's a lot of built-in models like normal distribution, log normal. We talk about like beta distribution. They are within Matlab represented by their CDF function, their PDF function, and in Matlab we also learned or demonstrated that if you know how to use help of Matlab, and then you also know which type of distribution you want to do, then you got some data. You can always fit the data into a known model. This one's quite important because we're probably going to use that a lot. Frankly, say you have tested some concrete, you came up with 20 tests, different strengths. Then you can fit it into a normal distribution, and then you can project what's the percentile of a very high percentile, which is probably not possible to do with empirical CDF because you don't have too many data points. But by assuming a model, you can do it. Then we showed it to you through demonstration that once you have your data fit into a model which you believe it's right, for the most part models are not right, but if you think it's useful or like good, then you can generate as many random samples from that model as you want. So up to this point, it looks like we are pretty good with modeling random variables and understanding how we can mathematically manipulate them. But first, then, like back to the whole point of this class, we still haven't talked about like what we're going to do with them at this point. Wait for that. We'll do that after like one more topic. But for now, before we even talk about doing that, we need to talk about the correlation and relationship between random variables. Why? You're like, come on, we already know how to like simulate them and all that. Why do we need to talk about relationships and correlations? The reason is that random variables, they can be related somehow. I mean, not this kind of related like a family. It's not. It's like they might not be totally independent. And for example, if you think back when we generate random variables using Matlab, using a normal distribution, and then maybe another one with a non-normal distribution, you generate them. When you generate one, it doesn't really know what's going on with the other one, so they are totally generated independently. But they are not all like that. So let me give you an example. So the example is, I'm gonna try to draw it. I'm using a mouse, so bear with me. It's not perfect. It's not, you know, Leonardo da Vinci stuff, but I think it'll work. So say if you're an engineer, right, then you are designing a water diversion tunnel between two lakes. We call this first lake Lake A, and then the second one Lake B, right? And then each lake, you know, they have different water levels over the years. You know, sometimes higher, sometimes lower. If you look at like each year or each month, yeah, let's say we're doing design, right? So we are doing design. So let's do like a year maximum water in A. What's the level? And the maximum yearly water level in B. What's the level? They are random. And then you may say, okay, yeah, great. So if I can say A, I got a mean that's you know, 30 feet, and then I took data from A for like 100 years, so I somehow get the standard deviation, and then I say, okay, that's like 5 feet, you know, so 30 of 5. Then on the B side we got another measurement, so yeah, this one's like a little bit lower, it's 25 feet, and with a standard deviation of you know, maybe this one is kind of a little bit weird, so it's 7. And then you're trying to design like how wide your like channel or pipe will be in between, and then it is somehow a function of the difference between A and B. So you're gonna say, okay, how I'm gonna do this? Yeah, let's just go do simulations. And I'm gonna simulate a yeah, let's just do normal distribution in A. I'm just simulate a whole bunch of numbers with this. Then in B, I'm gonna generate a whole bunch of numbers with this. Then I'm gonna just subtract those two, and then I got that delta, and then I'm gonna use this distribution of this delta to determine my D. Is there a problem with it? I'll let you think about it, but I mean, yeah, that's yeah. If it's a real class, I would say, hey, like this student, you tell me what you think or whatever. But you just think about it. The answer, if you have it, is it's not right to do this. Why it is not right? Because considering A and B, they are, you know, you're gonna build a tunnel in between, so they won't be that far away. They are in the same region. So when there's, you know, rain, the weather in the same region is kind of the same, right? You got the rain coming down. When A becomes water becomes very high, there's a very good chance that B, the water is also kind of high. And then when there's a drought, let's draw a song. Gee, okay, well, you haven't had a rain for, you know, 3 months, whatever. When the water level in A is low, it's very likely the water level in B is low too. So if you just generate A randomly and independently generate B randomly, and then do a subtraction, your delta can be a little funny. It's probably not a reality. So then naturally the next question is like, okay, well, if that's the case, what it is? Okay, let's try to talk about it. Hold on, what I'm doing. Okay, here. So the way we approach this is look at relationship between two things, or two random variables. Let's call them not A, but X and Y. Okay, you can think about that as water level in A or water level in B. For example, there's a different level of relationships. It's just like, you know, your brother and sisters, or you're just Instagram friends. So brother and sister type, like blood relationship, direct correlation, or not even correlation, it's just direct relationship. The strongest you can get between two variables are functionally related. So you can have, like y equals to x squared plus 5. And x, you can get y, y, you can get x. In the term of like that two reservoirs, you can see, maybe water in level A, in Lake A, is always 10 feet taller than Lake B. So A equals to B plus 10. I mean, it's not possible, but yeah, mathematically you can do that. And if you have that, there's nothing random about it. Even if like one variable is random, you can always deterministically calculate the other one. In fact, in our next topic in this class, where we talk about function of random variables, we're gonna specifically talk about that. Like if you know the distribution of like x, and then you know a deterministic functional relationship between x and y, then what is the distribution of y? That can be like totally closed form derived, so no problem there. On the other end of the spectrum, you don't even know that person, even through Facebook. You have no relationship. He's not totally another outside of the range of your, observable universe. Then we see X and Y, they are totally independent. If that happens, you can, actually generate X and Y totally independently and do all the simulation you want. But there's something in between where it covers like a whole bunch of stuff. That means, between X and Y, we don't necessarily were able to find a functional relationship. Maybe there is, we just don't have the function, or for some reason, just we don't have a function for it. But if we collect the data, like when we collect the X data, just make sure at the same time you collect that X data, you also collect the Y data, and you keep doing that. After you did that, a gazillion times, or like, not really a gazillion, but maybe 100 times, you look at the data, you find, oh, you know what? They are somehow correlated. So that's what we're going to talk about today. How do you mathematically represent or model that? Our water level in reservoir A and B surely will fit in this category, because if you collect the data from two reservoirs for 100 years, the maximum water level in A and B, they should be correlated. Like when A is high, B is high. When A is low, B is low. Like in any given year. So how do we mathematically model it? Wow, you're like, oh, yeah, this is totally. If you took my other class, which is about how to do presentations, this is totally not the way to do it. But yeah, come on, this is a class. So anyway, the way we used to model this type of relationship is called covariance. And then we can calculate a coefficient, which is called coefficient of correlation based on covariance. So let me tell you first how to calculate covariance. Covariance is actually just variance. We know how to do variance already. If you don't know, just go back and look at your notes. Okay. To do covariance, you have to collect your data in pairs. Well, that's a prerequisite. If you want to study a relationship, you have to collect your data in pairs. If you don't do that, you cannot study a relationship. period. Okay. So if you do that, you collect them in pairs. Then first you want to just grab x, all the x, and then just throw y away. Just assume x is just by itself. Okay. You calculate the mean, which is here. I signify as ex. And then you do that same for the y. So you got the y, you got the mean of y, which is ey, which is expected value of y. And then you also do that for variance. You know, variance, we're not talking about standard deviation here. We'll talk about variance. Okay, that's standard deviation squared. And so you do that as if they're totally not related at all. You calculate those numbers and keep them on the back of your file. Then you go in for each pair. Now you do x minus your expected or mean value of x times y minus mean value of y. Don't do absolute or don't do anything. Just let the signs carry. You know, if this is negative, this is positive, that can would be negative. Yeah. And then you just add everything up and divide. Say you have 100 pairs. You do that for every single one of them and add them up and then divide it by your total sum by 100. That is the covariance of your sample pair x and y. This is how you do it when you have like 100 pair of data. But you know, mathematically, you know, you need to do this through integration, given a what they call that multivariate PDF. But I mean, yeah, we're not gonna do too much of that. This is an engineering class, okay? Not a mathematical class. So just think about you're doing the covariance using data. If you have a lot of data, it's pretty good, okay? And then if you look at this, you think about it, right? If x and y, they are changing kind of together, like when x is bigger, y is bigger, then this product of those two differences are very likely to be positive. You think about another situation when x is smaller, like x minus mean of x is negative, then y is more likely to be also smaller. So this will still come out to be positive. So if x and y, they move in sync together, kind of, you're gonna get a pretty positive covariance. On the other hand, if x and y, say when x is bigger, y is lower. When x is lower, y is bigger, then those seems to be more likely to be of opposite signs. Then you can end up with a negative covariance. Then once you get to covariance, which is actually right here, COV of x and y, all you need to do is calculate the ratio between the covariance and the I say square root of the individual variance multiplied together. In another word, you can actually write it as a standard deviation of x times standard deviation of y, and this value, with all the data that is possible, will be ranging from -1 to 1. Then you say, okay, what does that mean? Well, we know the best you can do with covariance is they'll be equal to this because it's 1, right? That's the case. Then you can be -1 if you're totally flip x and y are totally not that correlated. The correlation of coefficient correlation, they always indicate some level of correlation when this is not 0. When it is 0, the sample pairs you selected do not show any correlation. They can probably be assumed to be independent, but you should always check. The reason is this. Coefficient correlation only represents the potential linear correlation or relationship, which means one's bigger, another's bigger, one's smaller, another's smaller. It's not a indication of a relationship, okay? Because there are nonlinear relationships that are almost perfect. Let me explain this a little bit. Those are the potential data pairs that if you plot them, you see them, and those numbers are the coefficient of correlation. So basically, you imagine each of those little cluster of point are on a coordinate system of x, and y. So for each point, it represents a data pair x and y. So you get one data pair of x and y. You put it on that coordinate system, you get 1 point. Like this point is like you get an x, then you get a y, get an x, get a y, everything's like totally on a line. It's almost like functional linear relationship. If that happens, then if you calculate the coefficient of correlation, you're gonna get a positive 1. The negative 1 you get it from it's a negative slope linear relationship, perfect. But anything from like perfect linear relationship, it's more like a line, but it's not quite. Depending on your slope is positive or negative, you get like negative 0.8, negative 0.4. If you get to 0, that means everything's just like scattered around. You can't really find any trend, linear trend. So that's when we say they're independent. Like one doesn't really affect another. In the middle line, yeah, just ignore this middle line. It just basically says this has a relationship or don't have a relationship, or and then the point is that you want to look at this final line. See if you have some data from maybe two data like a sunshine on a plot of land on Mars, and then the carbon content in that plot. You collect those, and then you do a coefficient of correlation analysis, which I will teach you how to do in Matlab. Then you came out to be 0. Okay, you're like, oh, they have no relationship. Wrong. Okay. You should always, if you spend so much time to actually collect data in pairs, you should always plot them to see if you can find something. Don't rely on just a number, because all those plots of those points, those pairs, they're gonna give you a 0 coefficient of correlation. But you look at them, there's something going on there. We're gonna talk about it later, but you might be able to get a better distribution model if you actually see those shapes, or maybe you can do a functional relationship between the two, and then just throw away one and just model another using random variable. So that's all can happen. So basically, know that coefficient of correlation, it is calculated this way. Matlab can calculate it for you if you have data pairs. And then it's only represent the potential for linear relationship. You should always check your data by plotting it. Really see it. Okay. All right. So now we're going to talk about Matlab, because I can talk about those theories and what you need to do all day long, but we do want to go back to our engineering application, which is like, oh, okay, well, yeah, you said you can't really generate those independently. You want a better delta, like, then what should we do? Okay, what should we do? Okay. So in Matlab, before we actually open it up, I'd like to tell you that, first of all, when we are handling correlated simulation, or like a couple of variables, there's 2 or even 3 variables that are correlated, we typically don't go too fancy with different models. We just do multivariate normal distribution. Then to simulate the data, you can use, yeah, if you stick to that, you can use a multivariate normal random number generator random function to generate your samples. And this function will actually generate samples in pairs. But to actually use this, you need the means of each variable. You put them in a mu vector, in a vector. So basically, if you have 2, then that vector you just tell them about the means. Then you need a what they call covariance matrix. So basically, what does it look like? We're gonna talk about that when we do our examples. Okay, let's do our examples. Yeah, let's take a look at our example. Yeah, well, we're gonna put this example here: 35 and 25, 7. Yeah, well, yeah, okay. Well, you know what? We'll get to it when we get to it. All right, Matlab. Okay, come up. So what we're gonna do here is we're gonna show you. Let me clear everything and see everything first. I'm gonna show you like it really makes a difference. Okay. So let's see. We have the lake A and lake. Oh, come on, lake B, and then let me copy down the numbers we have there. 30 and 5 and 25 and 7. Okay. So I have a mean of 30, of standard deviation 5, and then a mean of 25, and I have a standard deviation of 7, and I'm generating like oh, what the heck, generating 10,000 samples. Okay. Then we'll call this our well, I just do C. C basically is our difference, right? So we're gonna do the A minus B. Okay, that's our difference. Then once we did that, we're gonna plot a histogram. Remember, you're like, why do we plot histogram? Because that kind of give you some basic idea of what's going on. And then yeah, since we have like 10,000 samples, I don't mind just do like 30 bins. And here we go. Let's take a look. So already. So as you can see, of course that's a bad thing about normal distribution is there's some like irrational numbers, but the difference kind of have a kind of mean of around oh, what the heck, I'm gonna try to yes, what's the mean of C? Let me take a look. The mean of C is about 5 feet, which is yeah, sure. And then the standard deviation of C is what? About 8.5 feet. Wow. So yeah, this C is quite volatile. It's have a mean of 5, around 5 here. Standard deviation of 8, some, yeah. But that is when we assume A and B, they are changing independently. So now let's do the correlated case where we have a mu vector, remember? So I'm going to change that to 30 and 25. Oh, that's our standard deviation. So now the covariance matrix. Now we need to input in variance. If the standard deviation of A is 5, the variance is really 25, okay? And then the 7, like 7 times 7, it's actually 49, okay? The maximum covariance, if you think about it, is 5 times 7 is 35. So we're gonna say, okay, let's say they're positively correlated, which means when A is bigger, B is bigger. The maximum we can go here on the diagonal. So basically, if you think of this covariance matrix, it's like the variance of A and A, variance of B and B. If you have studied matrix analysis, this is variance of A and B, the variance of B and A, which should be the same, and it should not exceed 5 times 7, which is 35. So let's do a pretty strong correlation. Let's do 30, okay? And then we're gonna, simulate 10,000 of them. All right, let's do it. So you see, I used the multivariate normal random number generator with this mean, this covariance matrix generate 10,000 samples. So I'm gonna do that and then just run it. As you can see here, yeah, you can see it. Okay, R becomes it generated the first variable in the first column, the second variable in the second column. So this is a 10,000 by 2 matrix. So now let's calculate C again. Oh, in fact, before we even do that, here's a good. Let's plot this, and then you see what I mean. Okay, so where is it? Okay, so yeah, you can see this is your A, this is your B, right? Or yeah, maybe vice versa, whatever. So when A is bigger, the B is also like to be bigger, vice versa. Okay. But what does it do to our differences? So let's call this calculation C1, which is actually R A minus B. Okay, so we do that, and then we'll do a different figure. Okay, we'll calculate C1, and then we'll do a histogram of C1, which is the difference we measure from that. So okay, got it. You're like okay, I got it. It's like a 5 and it's yeah, I remember. Okay, it's still 5, right? So let's take a look at the mean value for C1. Okay, it's 5.350. Okay, you're like, okay, well, hold on a second. What's the mean value for C we just did? They are not that different, right? Okay, but the difference is in the standard deviation. The standard deviation of C1 is much smaller than standard deviation of C. So standard deviation of C1, which is from the correlated case, is 3.8. The standard deviation of C, which is from uncorrelated case, is 8. It's like more than twice. But then another way to see it is actually I'm gonna do histogram of C on top of C1. Okay, let's do that, and then I'll add a legend, and then you're gonna see the difference here. So C1 is the blue, which is the blue here, but it's gonna get covered by here, so it doesn't matter. Then C is this one because it has a higher standard deviation, so it kind of spread out a little bit further. Then you're like, oh, okay, well, I got that, but what does it say to our design? That makes a huge difference. Because if you want your design to handle, like, say, 90% of the case of the workflow, like the difference. So you want to find the 90th percentile of this delta distribution. If you don't consider correlation and just do the C, you're going to be designing for somewhere around here, like maybe you design for a delta of 25, the water level difference of 25. But if you consider the correlation, you only be designing for C1, which is for 90th percentile, which is like 90% of areas here, 10% here. You're gonna only be designing for like maybe 13 feet. So 25 feet versus 13 feet. You're gonna save a lot. That's the implication of correlation in our engineering design. I'm gonna give you another example. Let's just change this a little bit. Remember I said that you always do script. Let's change it up a little bit and see what happens. Let's say those two guys are like opposite. They're moving opposite. I don't know why. Like A and B, when A is big, B is small. When B is big, A is small. So they have a like negative covariance. Everything remain unchanged and everything. Then I'm just gonna do everything like, okay, I'm gonna like redo it. Let me close the plots. Oh, I already closed the plots. Okay, great. So I'm gonna just like redo it. So the correlation thing changed, and then now you can see it's like the negatively correlated. And then the difference C1, it's a different story, right? They are becoming a little bit more similar. Oh, actually, C1 becomes like a bigger spread. So remember, the C is when you don't consider any correlation. Then if you want to design for the 90th percentile, you're gonna go here. Like remember, yeah, it doesn't look too much because the scale changed, but you're still gonna go here about 25 feet. You're gonna design for that. But if you consider they are negatively correlated, like it's almost like they are intentionally trying to make their differences bigger, then you simulate your 90th percentile will be around 30. So that will make a direct impact on your design decisions. Okay. So I guess the next question is how do you if I have data, okay, well, yeah, I know that if I have data, in fact, if I know the mean of the data, which I can easily get, and if I know the covariance, I can easily calculate based on the formula I give you somewhere here. Okay, yeah, basically description I give you. Then I can actually simulate with in Matlab, you know. So that's pretty cool, assuming everything is multivariate normal. In Matlab, they also kind of give you tools to calculate correlation coefficient, correlation covariance. So you just use the help file, you know, covariance. Yeah, in fact, you know, function COV. Okay. Covariance of A and B. Okay, let's say covariance, return the covariance between two random variables A and B. Okay, well, let's try it out. Let's try like say covariance between our A and B. Remember, we simulated them independently. You guess what's the number going to be? Oh, in fact, they actually give you the coefficient matrix. It's this, which is pretty close to what we have, 25 and 49. You're like, oh, they're not the same. Yeah, this is calculated by data. That's, you know, and this is almost zero. But if you do covariance of, let's see, the, not C, what am I doing? R, okay, covariance of R1 and R2. You know, I generated with, you know, negative 30 here, so we should get something pretty close. Yeah, almost that. This is how you do covariance in Matlab, if you have data. Okay, I'm gonna, you know what, save this in the statistic folder. Okay, this is let me save it. So, and I'll send it to you. Okay, so study covariance. Okay, all right. Okay, we're done here. That's what it means. When you need to simulate things together, you do this. Okay. We tried out our example, and now we got a homework. Oh, yeah, you're like, oh, this guy's doing homework online. This is bad. So as a graduate student, this is a graduate-only class, so I expect everybody to be able to do some self-guided research. It's a simple question. So we got a coefficient of correlation, right? We introduced it here. Is that the same as coefficient of variation? Is that same of R square value? Because this guy in linear regression is also from -1 to 1. Are they the same? If not, what's the difference? Okay. So write a brief research result and send back to me via email by, I give you about 2 weeks. And feel free to use any source you want. Wikipedia is pretty good. You can copy and paste all the material or reference you want. Just tell me where you copy them from, okay? But do a summary of similarity and differences using your own word. It can be just a paragraph. Like you can use some bullet points or whatever you want to use. Like half page, 1 page, I don't care. Just make it brief. Clearly mark it as my summary. You have to write it yourself. And after I review it, I will have you guys to share your thoughts. What I'm doing in class sometime when we meet. Okay, that's it for this class. We'll see you in a little bit.